I have the now pleasure of introducing Gillian Hadfield. Gillian is the inaugural Schwartz Reisman Chair in Technology and Society. She's Professor of Law, Professor of Strategic Management, all at the University of Toronto, and also holds a CIFAR AI Chair at the Vector Institute for Artificial Intelligence. She is a Schmidt Sciences AI 2050 Senior Fellow. She was the inaugural Director of the Schwartz Reisman Institute and Society from 2019 through to 2023, about to move to Johns Hopkins in a very, very exciting move, so keep your eyes peeled for that. And her research is focused on the study of human and machine normative systems, safety and governance for artificial intelligence, and innovative design for legal and dispute resolution systems in advancing and developing market economies. She's also long studied the markets for law, lawyers, and dispute resolution and contract law and theory, and she teaches about contracts and governance of AI. One of the things it doesn't mention on this little bio is that Gillian is also a trustee of the Cooperative AI Foundation and has been really, really instrumental in the kind of setting up of that organization, the kind of growing of this field, and so really one of the kind of key voices who's been thinking most about some of these issues for the longest time. So I'm really, really excited to be able to have her to talk. And Gillian, over to you.
Thank you, Louis. Welcome to the SAFE family. This is going to be a pretty pedagogical talk, but Louis and I chatted before. But I do also want to try and do some inspiring just to join us in this work. This is really important and fundamental work, and I actually wanted, through the course of this talk, convince you that thinking about this challenge of how to build normatively competent AI, which is the subject of my Schmidt Sciences Fellowship, and really the focus of, where my research over 7 or 8 years has now started to focus. I really want to convince you that it's not just a feature to think about cooperation as a subset of things that advanced intelligent AI systems can do, but that actually cooperation and thinking about how do we achieve cooperation is actually at the foundation of building general intelligence. So I want to try and get that into your head so you can see this as something that, if you're really interested in the areas of AI and how we build intelligent, how we build safe and beneficial intelligence, I really think that cooperation is at the heart of that. So when we think about cooperation, most of us, my PhD is in economics, so that's my original training. Most of us think in terms of pictures like this, the prisoner's dilemma. We have two by two grid, we've got payoffs, and we're trying to analyze what could cause these agents to cooperate. We know that in the absence of any, if this is a one-shot game, we got rational players, then we're going to have that defect result. And so most of us, when we're thinking about cooperation, again, think about how could we try and get to that defined cooperative outcome where there's cooperate, and we get that higher payoff. But we think about that in the box. We think about that with, for example, tit-for-tat strategies, where you can think of that as second-party retaliation, or we can set up structures like that to achieve that cooperation. Now, the way I've been thinking about cooperation for many years now is to say, this is not actually how humans solve this problem. They do in some cases, but for the most part, humans solve the cooperation problem by embedding all of those individual games in a broader context and establishing cooperation norms. So many of the people who are sitting in that interrogation room, when they are thinking about, do I rat out my co-conspirator or not and take a trade-off, they're not just thinking about a little grid like that. They're thinking about what people outside the room are going to respond. How are they going to respond to how they pay, and what kind of consequences might be experienced from the third parties, from the community. And the key method that humans have used throughout our history for enforcing norms of cooperation, kind of soup to nuts through all our interactions, is to ultimately exclude people from the benefits of being a member of a group. right? If I don't hire you, I don't do business with you. Literally, for many, many millennia in human history, literally kicking people out of the group, outlawing them, send them to the forest, etc. And I think that many of our steps along the way, the things that we're reactive to when we get messages that we've behaved in ways that are not considered appropriate in the group, like being sensitive to criticism, like being sensitive to the group sort of sitting you down and yelling at you, is a consequence of when those things happen, you should update your estimate of the likelihood of being excluded from the benefits of the group. So this makes me focus on saying if we really want to understand cooperation, we really need to understand not those primary games, like the prisoner's dilemma, but rather the games in which they're all embedded about how we coordinate and incentivize third-party enforcement of things like a cooperation name. So that the real game, I think it's really interesting to pay attention to, is the A and B game that says, should we punish or not this third-party norm violator? So that enforcement game. Cooperating on enforcement vastly expands the set of attainable states and solutions. Any of you who've worked with like those little prisoner dilemma games or versions of that know that they're quite sensitive to the payoff structures, to the information sets. But if you embed them in the enforcement game that says, here's how we play this game, and if you don't play that game, you're going to suffer third-party punishment, and we've coordinated that enforcement game, we can achieve a lot more outcomes. And I think that's the evolutionary story about why it is that humans have landed on this method for solving cooperation challenges. Cooperation on enforcement facilitates the stability of groups, and that's really important because the stability of our groups is what generates the capacity for exchange between agents. So specialization in the division of labor between humans, cooperation on tasks, that exchange generates increased surplus to the group. So that's the benefit. You get a group benefit if you can maintain the stability of your group. You maintain the stability of your group by saying, and here's the rules of our group, and we're going to cut you off from this surplus that we generate if you don't do it. So in fact, it's a technique that you can imagine using as well as, create a club, generate surplus in the club, and then the stick you have for enforcing the rules of the club is exclusion from the club, right? So I think that's kind of the core way in which we've structured cooperation in human societies. Now, if I want to dig into how humans have solved this problem of achieving group stability to support exchange, and my analysis is focused on thinking about how we've done that with shared normative classification and how we've incentivized and coordinated third-party punishment. So I view these as the primary problems for us to think about. And then specific cooperation challenges are secondary or derivative of that. And as I've mentioned already, I think this is the fundamental question of human evolution. How did humans achieve ultra-cooperation? Now, I'll say we often sometimes talk about our concerns about the failures of cooperation in human societies, and we see lots and lots of examples of that. But it's really important to step back and say, nonetheless, humans have a level of cooperation that's just off the charts and unseen in any other species. We have ants and we have bees, which have, high levels of cooperation, but it's in very defined settings, right, to accomplish very specific tasks. We have the capacity for enormous levels of cooperation. I always like to say, just look around the room you're in. The amount of cooperation that sustains being able to do this. The building was built by somebody else. The food was prepared by somebody else. You flew here on planes that somebody else built and flew, and airports that had power supplies that were or not right. That there's just an enormous level of cooperation when you think about that cooperation as the fundamental cooperation that underlies a market economy, a political system, et cetera. All of that is cooperative activity. So how did humans do that? Well, I've been thinking about this question for well over a decade and trying to work towards building as an economist, I call a positive theory. So positive versus normative. Positive means predictive in this sense, right? It's explanatory, it's predictive theory, And ideally, it's parsimonious theory. That's another thing I get from my economics training. I sort of want the most parsimonious model of humans and the most parsimonious model of their situations to be able to powerfully predict what might happen in different circumstances. And together with Barry Weingast, political scientist at Stanford, we started building those models, published a first paper called What is Law? In the Journal of Legal Analysis in 2012, and then have a review paper from 2014 that compares our theory of what is legal order to all the other theories that are out there, sort of philosophical theories, sociological theories. So if you're interested in sort of an introductory piece about that, you might find that helpful. The actual model, a simple version of the model, is in the first paper. And one of the things we're doing with building this theory is, let's say, providing some crisp definitions of what we mean by all these elements. I often find that when we're having conversations about safe, beneficial, cooperative behavior in AI systems, because it's often we're a lot of computer scientists in the room have focused on computer science and not social sciences. And maybe even some of our social sciences, we often don't have very crisp ideas. We use the language of norms, values, ethics, common sense morality, et cetera, but it's really fuzzy. And I want you to know that being a social scientist and economist, that's not where I'm coming from. This is not about there's some fuzzy concept out there that, it's either something undefined that's in the brain or it's just something that happens. Right? When I'm building theory here, I actually want to build very crisp definitions. I think I just encourage you to also don't use fuzzy concepts. If you're going to use a concept if you're going to talk to me about common sense morality, like somebody else in the retreat was a couple of days ago, I'm thinking, what is that? Or culture? People like to say culture. Well, what is that? What's your theory of culture? Right? And we actually have theory of culture built up from these pieces. So let's get some definitions. So normativity. We define normativity as the human practice of classifying behaviors as appropriate, not appropriate, and then channeling behaviors to appropriate. So it's a binary classification, appropriate, not appropriate. And when if it's helpful to you, you can redefine punishable, not punishable. This we criticize, this we don't, as a collective, right? So punishable or the binary classification. And then we define a normative social order as an equilibrium supported by community third-party enforcement of behaviors classified by the community as not appropriate. So we have a means of classification, and then we've coordinated enforcement by third parties around that classification. So that means that I want to think about a normative social order as having two key institutions or mechanisms. The first is a classification institution. Classification institution is either a process or an entity that is producing the classifications. Now, those could be completely emergent. So think very small groups, repeated interaction, fairly homogeneous, stable settings. And it could just be that behaviors over time have settled into, we build our arrows this way and not that way. We say these words and not these words before we eat. We cook our foods this way and not that way. And we criticize people who do it differently. Like you could go into those communities and you could observe there's clearly a way to do things here. But there's no specific entity that's announcing what that is. And my view of human evolution is that it's the evolution and the pressure that we experience as societies grow and become more complex because they innovate, they have new members, environmental conditions change and so on, that there's pressure to actually develop an institution, an entity that will perform the function of reducing the ambiguity of classification and supplying new classifications when there's new novel things. So you can see that as sort of a list that goes down into more and more formal processes. The other piece of a normative social order is an enforcement mechanism. So if I'm theorizing about a setting, I'm saying, okay, what's the third-party enforcement mechanism here? And throughout most of human history and still throughout most domains, it's the behaviors of ordinary members of the group, ordinary individuals. It's not an enforcement apparatus. So don't be thinking enforcement mechanism means you must have a police force. That's very late in human history, and they actually only get engaged on a subset of enforcement. Again, we have sort of increasing levels of formality, from making fun of people who don't do things the way we do them, criticism in the group, exclusion, as I mentioned. And then we can say, oh, it would be good to have specialized enforcers. We'll all contribute some tax dollars, and we'll have entities like police forces. I now want to define something I call normative infrastructure. Normative infrastructure is the institutions, behaviors, and cognitive architectures that support that normative social order. So a classification institution would be a piece of normative infrastructure. And now, heading towards sort of my announced goal for this talk is the idea of normative competence, which is the capacity to perceive, predict, participate in normative institutions and behaviors. Humans are tremendously competent at normativity. We are really good at going into a new room and saying, okay, how do we do this here? How do we manage things like masks? How do we manage things like how we eat, how we talk, how we interact? So I started thinking about this in an early paper in 2017, co-authored with also my son, Gillian Hadfield, based on a classic problem from the Amadei et al. Concrete Problems in AI Safety, which I assume you've all maybe looked at, but you should if you haven't. And they propose a challenge. Here's a challenge of safety for training AI systems. You train a robot with a reward function. This is pre-thinking language models that do everything. With a reward, using reinforcement learning to learn a path carrying boxes from one side of the room to the other. If you train that, and the problem that Amadei et al. were posing is if you train that robot with that reward function, +1 for every box you get to the other side of the room, it's going to develop a policy for an efficient path to do that. But then if you deploy the robot into an environment that has things that weren't present in the training data, like vases that all of a sudden appear on the learned path, what is the robot going to do? Well, the robot's going to plow straight through the vase because it doesn't know anything about vases, right? And this is sort of an incompleteness problem with the specification of what it is you want the robot to do. So when Dylan and I started collaborating on this, and I'd done a lot of work on thinking about principal agent contracting for humans, so I said, well, let's suppose you hired a human to carry boxes across the side of the room, and you gave them the same reward structure. I'll give you $1 for every box you get to the other side of the room, right? They're going to look at the room, they're going to evaluate it, they're going to come up with their strategy for accomplishing that. They've got the same reward structure as the robot, but if a vase appears in the room after the employer's walked away with the human agent, what's the human agent going to do? Human agent's going to walk around the vase, right? The human agent is not going to plow through. Now, why does that happen? Why is it that the human agent responds differently, even though it's got the same reward structure? And the answer is that humans are actually doing something. When they see that vase, they say, oh, wait a second. If I stay on my usual path, I'm going to knock over that vase. And imagine, expensive vase, going to break, etc. I'm going to knock over that vase. What happens then? Well, they start thinking about, well, maybe there's laws about that. Maybe my employer will be able to legally withhold money from my paycheck to compensate for the damage to the vase. Or maybe I'll get sued. Or maybe there are just consequences from social responses. Like I get a bad report on my as an employee, and it makes it harder for me to get jobs. Or the other coworkers say we're not working with you anymore because nobody knew who crashed into that vase, and we don't want you on our team. So what that means is that for the human, the reward function is actually implicitly filled in with that infrastructure with this, oh, there's actually a cost associated with taking the path that we usually do. And when I teach, and I've taught contract law for, I don't even want to say it, over 30 years, although I won't anymore at the Johns Hopkins University. I'm joining the School of Government and Policy. This is what I'm teaching budding lawyers, is how to do contract law, and it's filled with this idea of the way we interpret and enforce contracts. They're always incomplete, they're always ambiguous, and we use techniques like thinking, well, what was it reasonable to think the parties had in mind? What would it be reasonable to do? That's filled in by external infrastructure that's outside the box. And this is a way of thinking about, economists have been thinking about incomplete contracting for many decades, and recognizing that, you know, this is like a wage function, or like a mechanism design, for example. Actually, those contracts are embedded in a scheme. There's all this external infrastructure to draw on to support the rationality of agreeing to contract in that you know, stripped down way. So here's that question: can we build normatively competent AI agents? Can we build robots that, like humans, are able to perceive, predict, anticipate what, you know, they say, oh, there's probably some rules about knocking over vases. I should try and see what they are. I should try and predict what they are. So that's what I mean by normatively competent agents. So I've now started working on this project in multi-agent settings, and thinking about how can we think about building normatively competent agents that are capable of engaging in the behaviors of enforcing the rules and then complying with the rules. Rather than, say, solving a problem in a multi-agent setting, we just say, oh, come up with your own policy for playing this game. Let's focus on that enforcement game. So this is a paper with a group of people from DeepMind, and also Dylan as well on this one. And it's in PNAS from 2022. And what we looked at here was training agents in a multi-agent setting. This is reinforcement learning agents. They're in an environment we call the poison berry environment. There's a whole bunch of berries, different colored berries. There's no shortage of berries, so we don't have any free rider problems in here, and we don't have you know, any congestion effects or anything like that. The only challenge to solve in this environment is that one of those colors of berries is poisonous. And if you eat it, it has an impact on reducing your health, but 100 steps out. So there's a credit assignment problem of figuring out which of these berries is making me feel sick and reducing my payoffs, my welfare. So what we've done is we created an environment where basically we as experimenters, we've imposed a rule on the rules in the environment where we've said, okay, we experimenters are going to establish that it's taboo to eat you can't even tell the color of the poisonous berry, the red one at the bottom there. So we've established a rule. Now, what does that mean? Because our agents are learning, they don't have any model of the world, they're not given rules, but what they are giving is rewards. And we established a structure that says if an agent eats a taboo berry, they change color, they become marked. They don't observe their marking, but other agents in the environment can observe the marking. So that's a bit like we can all look over and point and say, that person over there, you know, they ate all the cookies on the plate, right? Or they ate the food that we don't eat. So the other agents can observe that the agent has violated the rule. And then all of these agents have a punishing technology. They've got a zapping beam. That's the yellow in here. They got a zapping beam. Now you can think of that as just an implementation of imposing some cost. It could, like if you want to think about it in real terms, it could be its criticism. But here it's a zap. And when an agent zaps, it's costly. It uses energy to zap. And if they just zap agents that haven't done anything wrong, the agent who gets zapped experiences a cost, and the agent who does the zapping is experienced a cost. And it's like, okay, we should learn not to zap people who haven't. But if they zap a marked agent, they get a reward. So that's a way of implementing the idea that somehow we have incentivized members of our community to enforce our rules. Now that's actually a fundamental problem for us to be working on. So this is a hack to just study what happens in an environment where there is an incentive to punish. So if they punish a marked agent, they get a reward, and so that gives them incentive. So when they just sort of start roaming around in this environment, they can learn that, oh, there are rewards to eating, there are costs to eating something, but I don't know what it is, and there are rewards for a certain kind of punishing, right? So what we wanted to look at was, do these agents learn to punish? Do the agents learn to avoid punishment, which means to comply with the rule? Does a stable state with this normative infrastructure? What's the normative infrastructure? It's the marking and the rewards for punishing marked agents, and some structure which is now just kind of hidden, and we've supplied as experimenters in the background. That normative doesn't emerge. And then we were specifically interested in this question, which I'll say a little bit more about in a minute, of does the presence of a silly rule affect learning, and does that normative infrastructure raise payoffs? So let me say a bit about silly rules. This is actually something that comes out of the theoretical work that says we often analyze which rules a community should have based on the specific rewards, payoffs associated with rules. We tell evolutionary stories that say that, norms will evolve, we'll have selection of the rules that solve problems. If you have an economics background or anything like that, you'll know that there's a lot of looking at norms and rules and say, okay, what particular challenge are those rules solving? But if you start thinking about the coordination of the enforcement game, you actually start focusing on the set of rules, the whole collection of rules. How are we coordinating agents to enforce any of the rules in our collection? So we define this difference between a silly rule, which is a rule that has no direct impact on welfare. Now remember, that's our definition. We're not trying to point out in the world and say, look, there's silly rules, and we've concluded they have no direct, I've just defined it. That's what I mean by the language of silly rules, no direct impact on welfare. Doesn't mean the community thinks it's silly. Could in fact be highly, highly meaningful and important to the community, but from an economic point of view, no direct impact. Contrast that with important rules that do have a direct impact on welfare. So it's, again, just a theoretical distinction to draw here. And then what we did is we ran an experiment with this multi-agent reinforcement learning setup where we had agents trained in 3 different conditions. In the first condition, there were no rules. There was just the poisonous berry and the punishing technology, and we looked at what they did. We then had an important rule condition where the poison berry was taboo. So that's an important rule because actually avoiding eating the poison berry has a direct impact on welfare. But then we also looked at environment. We said, well, let's add a silly rule. Let's also put a taboo on a totally harmless berry. And most of you would think, well, why would you want to do that? If I ask you the question, do you want to live in a world with just the important rules, or do you want to live in a world with a bunch of silly rules as well? I think people's instinct is, well, let's just get rid of the silly rules. Why are we doing those? But this theory says, actually, you want to be in environments with silly rules because they are more stable and they learn better. So here's what we found. These are the plots. The yellow lines are that's the no rules condition. The green line is the red line is the important rule condition. So the poisonous berry is the only one that's taboo, and the green line is the silly rule plus the important rule. And if you just want to take a look at the final, the bottom right here, panel F, that's collective return to the group. And what you can see from that flat yellow line is the credit assignment problem is too hard. Agents never learn to avoid the poisonous berry. You can see that with the red line, which agents are punishing, they get a reward for punishing agents that have eaten the poisonous berry. We do actually see an increase in welfare from that. But the green line with the silly rule as well, the agents at first are spending a lot of resources on, because there's twice as many berries to punish, and that's a little bit more confusing, but eventually they do better. And you can sort of see this in this plot a bit easier. The agents with the silly rule, they engage, on the vertical axis is how much punishing there is of marked players in early stages, and the horizontal axis is the amount of time that agents spend poisoned in later stages. And so what you can see is that the silly rule set populations, they engage in more punishment early on, but they experience lower rates of poisoning in later stages relative to what the experience is for the important rule only. Okay, so now I'm going to tell you a little about some ongoing projects as we try to sort of take this setting and think about, can we figure out if normative infrastructure helps agents generalize aligned or cooperative behaviors in new environments? This is related to this claim that this is fundamental to general intelligence and cooperative outcomes, that you actually want to train agents for general capacity that they can take into other environments, and you do that with normative infrastructure. And this is folks from my lab. Rakshit will be doing something later in the summer school, so you'll get a chance to meet him. And Dylan and Will Cunningham at U of T are collaborating with us. Okay, we call these experiments the altar experiments. I'm using the idea of the altar as a focus of attention, a central place, a sacred place that helps us understand who are we, what are we allowed to do and not allowed to do in our environments. But the idea of a central location, that's a piece of normative infrastructure. So what we're now thinking about, still think about this schematically as the poison berry setting. Can we train agents to learn to punish what's on the altar rather than punish agents who eat blueberries? Previous study I just showed you was like specifically train them to punish whatever we have marked as taboo. But now we want to, can we get this more general? Can we say whatever is on the altar, and even if the behavior that is supposed to be punished on the that's represented on the altar changes, do they sort of continue in that behavior? This is a key part of the definition of legal order that Weingast and I proposed in that early paper I pointed you to. And that was that what's fundamental about legal order is because you have a defined entity that it is common knowledge, all the agents are looking to, we're all looking to the laws that Congress has passed, or we're all looking to the decisions the elders are announcing, or we're all looking to the proclamations from the monarch. I know that you know that I know that you know, et cetera, that's where we're looking for our prediction of what are others going to punish? I've just seen a classification of punishable behavior. Do I think others are going to punish? I don't want to be the only one punishing. Are others going to punish? Right? And that's what we mean by a classification institution. This altar is, and one of the things we were saying about the fundamental point about law is with a defined institution that's doing that, societies have gained a tremendously valuable tool for adaptation, because they can change their rules, they can change their classifications without disrupting the stability of their group, without breaking the equilibrium. Because the equilibrium is based on, I can predict everybody will help enforce whatever rules are announced by the ruler, rather than these specific ones. So that's the point, that this is a tremendously valuable bit of normative infrastructure for a society to develop. So we want to know, can we train them to do that? That would, as I said, give us the capacity to alter the content of what our rules are. Today it's blueberries, next week it's red berries or whatever. But could it also give us, we want to test also, does it give us the capacity to see whether or not agents trained with that normative infrastructure, with an alter in one environment, are able to generalize, put them down in a different game, take them out of the poison berries game, put them down in the allelopathy game, for example. And the allelopathy game is one where there are benefits that you have multiple berries you can plant, for example. But if everybody plants the same color berry, we get higher rates at which the berries spawn. And so we benefit if the whole society is planting the same berry, has a monoculture, right? So could we take agents trained in the poison berry environment and stick them down the allelopathy game, or a tragedy of the commons game, a pollution cleanup game, any kind of other game? Will they be able to generalize that behavior there? And so that's the line of research that we're currently working on, and we're using the melting pot cooperation substrates that I'm pretty sure SAFE has sponsored. Let's see, is Lewis here? I'm not sure. Anyway, David may know. I believe that's something that SAFE is sponsoring. It's a suite of cooperative games where you've got agents and you can go in and it's competition. There was a competition in Europe last year around this, for example. So we have some very early results from this, very early. And we've actually, our starting environment is the allelopathy setting. I think it's probably just too dark to see, right? What we've got are 3 different colored berries here, red, green, and blue. We have agents that can zap. And we have the agents, the monoculture, you do better if you plant all the same color. Some of the agents would rather that we all plant red berries. Some of the agents would all prefer that we plant green berries. Nobody would prefer that we plant blue, but they would prefer we have a monoculture of blue than a mix of all the different colors. And there's some nice papers in the literature looking at this kind of game, looking at could you get an implicit, like if you have an intrinsic reward for punishing what everybody else punishes, can the agents get to, and it's a very nice Vinitsky paper on that. So what we've introduced in this environment is an altar, and that's what that square in the middle is, and that what that represents here is red. We all should plant red berries. Again, there's no communication of that to the agents in any structured way. It's only representative of the rewards for punishment. Agents, when they plant a color berry, they turn that color for a period of time. So agents will know, I know you just planted a green berry. And agents will randomly turn gray if they plant, the way they get rid of the gray color is by planting, and that's sort of signaling free rider, because if you just ate berries and you never planted, right, you could avoid getting punished, you get the benefit of eating, but you're a free rider. So we look at 2 conditions here. One is we call the hidden rule condition. That's like the silly rules game I showed you. That's where there are rewards for punishing agents that have planted blue, have planted green, or who are gray. And we have an alter condition which has exactly the same reward structure. The only difference is it's got a representation on that square in the middle. And if an agent visits the altar, they get an observation. Oh, there's this feature in the environment that has red on it. I get that observation. But that's the only difference. And so what we're interested in is what happens here. And what we're able to see in these very early results, the red line is the alter condition, the green line is the hidden rule condition, and the blue line you can just ignore. It's sanctioning without any rewards for anything. And the vertical axis in the top plot is the mean return. And what you can see is our agents with the alter, even though it's exactly the same incentives and payoffs, agents are doing better. We have not yet quite figured out how to explain this other than to say it seems that the agents are better able to learn about the rewards for punishing. What should we do? What should we punish? Because that's the hard question. What should we punish? If the agents get coordinated on punishing, compliance just falls out, right? That follows. So that's why I say that's the initial challenge there. I think these are what we look at is at different iterations. I think this is too hard, and we haven't yet got the monoculture graph, but what we can see when we spend a lot of time staring at these pictures is that the alter agents achieve a monoculture more quickly. So they spend a longer period of time with the benefits of the monoculture. That's what's being represented in that mean return. If you just want to, it's fun to see what it looks like, but I don't think it's going to be meaningful how these things. One of the challenges we've got is we still have agents that are just kind of firing randomly because we don't have any costs associated with firing randomly, and that's a fix we need to get to. Okay, all right. Last bit here. We're also trying to look at this in the context of generative agents. So I don't know if you've seen this or heard of this paper, just from last year. It's incredible how fast things are going. This is a simulacra. This is like called Small World. It's got a bunch of agents. The agents are just calls to a language model. And so and in this initial one, they just roam around, they plan Valentine's Day parties, they decide to attend or not attend the party and buy decorations and just talk about who they're going to vote for mayor and so on. And the structure of this is that the agents are getting this agent architecture, which hopefully you can see it's quite small, I realize at the bottom. The agent architecture, which takes in the stream of observations of all the things that have been said, all the things that have been done. I mean, everything's being done in text. But they process those observations. And they process them and select some of them and say, oh, that was an important observation. Somebody said, let's have a Valentine's party. And then you query the model, to sort of ask the question, is that something I should pay attention to, right? As opposed to an agent that just said, I got up at 7 a.m., right? Is that important or not? So they process that. That creates sort of a more limited set of observations, which are now going in as prompts for the next actions for them to take. So we're interested is, can we design generative agent architecture to include learning and implementing normative perceptions, reflections, plans, and behaviors? And do such agents learn to follow rules, use an alter to coordinate their punishment actions, generalize to new environments, and devise normative infrastructure? So that's kind of the holy grail out there is, okay, can we get these agents to not only use an alter or that normative infrastructure, but then actually participate in, let's meet around the fire and talk about what our rules should be and should we change them, which is how humans do it. I have a paper on sort of how this works in the gold rush in California when everybody arrives and starts digging for gold. So what we've done is we're exploring whether or not creating what we call a normative module in the agent architecture helps these agents do a better job of organizing, coordinating around normative infrastructure. So in that, so in this environment, we've looked at two settings. We've looked at one here, represented here, where there's multiple alters in the environment. There's multiple entities that are saying, here's what the rules are. This is about picking, apples or berries or bananas. So you've got various entities that are sort of saying, hey, we should pick apples. We're supposed to pick bananas. And we have background agents that are hard-coded that they're paying attention to one of those alters. And we have a new agent coming into the environment, the foreground agent, that needs to figure out, what should I do in this environment? What do I pay attention to? So the normative module is taking this stream of observations and asking questions. I know you can't possibly read that. I don't think I can read it without my glasses on. Does this observation contain information about a classification institution in the community? Will I be criticized by the community if I do this? Plant berries. Will the classification institution classify this behavior, planting berries, as sanctionable? And using that as a way of processing the observations. So we're looking at can a generative agent learn that a set of hard-coded background agents, which alter they're using, and that's the multiple alters version. And then we also have what we call the unreliable version, where we have an entity that purports to be announcing what the rules are, but none of the agents are actually paying attention. And this actually reminds me of work I did in Slovakia in 2003. You've got the change from a networked, socially planned economy to a sort of more Western style, legally based market economy. And I was surprised to say nobody was paying attention to what the whole bunch of new law, but nobody was actually paying attention to it. They were still following the rules from the previous regime. So we're doing prompts here to GPT-4o. Things like telling them what kind of situation they're in, try to be a good citizen. It's generating it's generating discussions, it's generating statements back and forth about sanctionable behavior, not sanctionable behavior, and then the agents are choosing what to do. And again, very preliminary results. This is in the unreliable alter case. The picture on the left is showing you results from the baseline policy without a normative module. The one on the right is showing you with the normative module. The vertical axis, we looked at different conditions. We said, are there 2 possible things you could plant, 3 possible things, 5 possible things, and then we're varying the number of agents, the background agents, along the horizontal axis. In this one, blue is better, because this is showing us the percentage of actions taken that follow the alter. Like, do what you're supposed to do. Do what the alter says you're supposed to do, but the agents aren't doing that, so it wouldn't be coordinated. And you can see that we do better with the normative module. And then when we have multiple alters, same structure here. Now red is better, because red is following the particular alter that the other agents, the authoritative alter that the other agents are following, background agents, and you can see we do better with that normative module. So I'm just going to conclude with, this is my favorite definition of artificial intelligence. The activity devoted to making machines intelligent. Intelligence is that quality that enables an entity to function appropriately and with foresight in its environment. I like this definition because appropriately is a normative term, right? And it's so once we say that's what we mean by behaving in an intelligent fashion, then we're saying, okay, doing what is normatively appropriate in a setting is what it means to be intelligent. And so that's why I say, to get AI to function appropriately, cooperatively, however you want to think about that, requires building the institutions, behaviors, and cognitive architectures, which meaning normative infrastructure and normative competence that sustain complex, normative social order in complex human societies. And I'm done.
Thank you.
Thanks a lot, Gillian. Just jumping into some audience questions. Can a small group of people exploit a larger group by coordinating amongst themselves to change the norms of the group, and how can we prevent this from happening?
Yes, so we have not started looking at that, but the answer is yes. They can, they have, they do. That's the story of human history, is capturing the classification institution, basically. So that's politics. And we have not yet started to study that type of question, but it's clearly on the path of what we want to study here. Remember, but what we want to do is figure out how do we analyze that in a way that is theoretically complete. So in fact, it might be that a small group capturing the institution, they may have actually better rules than we would get from a large group. We don't know that. So one of the things we want to think about is precisely how well do those kinds of structures work. The theory of democracy, there's an epistemic theory of democracy that says actually the shift to that kind of institution, not leaving it up to the kings and queens and their advisors, but rather having broader based input into the rules and control over the classification institution, does better because we get better information about the economy. We move to better rules. But that's a separate challenge, and I wouldn't start with the presumption that a small group is going to take it and take advantage, but it's absolutely part of what can happen here. So that's part of studying what would be the best normative infrastructure for us to develop, and would it be sustainable? Would it evolve? Would it generate welfare?
Next question is, as you mentioned in the zapping experiment, you implemented a hack. What's stopping us from representing those important parts of rule building faithfully?
So the hack in the silly rules game is that we've just said where the rewards will be for enforcement behavior. But what's stopping us from not hacking that, right, and actually endogenizing an incentive to punish is that's what research is all about. You have to solve so you need to, on a new agenda, you have to solve the problems you can solve first and then build your way to that. The original paper that I pointed to from 2012 actually does have an endogenous incentive to punish, which is a very nice one. I really like it. It's a signaling story. So there's actually no free riding in that incentive. But this is just, these are all problems we need to solve. That's why more of you should work on this agenda, so we could have lots of people working on it, and somebody can take on that challenge of how can I endogenize that incentive to punish.
Thanks. And next we have, how can we achieve cooperation between groups with clashing norms in anarchic settings, e.g. international relations?
Yeah. So when I talked about this like there was a single group with a single classification institution. That describes, so I'm doing work right now studying the behavior, how the system of elders works among the Turkana of Kenya, which are a very defined group. It's fairly homogeneous, and it's like, here's the group, here's what we're coordinating, and we have a single classification institution. The worlds we've evolved to have lots of overlapping groups so that we could think about the normative social order in multiple groups. And I think it's part of the story of human society is that expanding group, right? From the family, the clan, the village, cities, larger collections, we get the formation of states, and now we think about the international community. What you're trying to do is exactly figure out how can we come up with the classification institutions and incentives for enforcement that coordinate this larger group? And if we think about solving that problem in the international setting, we're saying, so part of, again, the sort of the original theoretical work said, what are the constraints on the classification institution that we have to satisfy in order to incentivize that third-party voluntary participation? And one of those was sufficient convergence between the interests of each individual actor and the classifications that were then going to define the equilibrium. So if we think about that in the international setting, it's like saying, okay, you can go to war and try and force your rules on another group, or you can look for systems that say, here's how you can get enough of what you want. What you want is all those independent players to say, I do better under this equilibrium than I do in my next best alternative. Anarchy, closing my borders, etc. So I think most of you want to think about this theoretical apparatus giving you a new lens to think about those kinds of settings. I'm not starting from any normative position myself that says, here's the best way to organize the world. I'm providing a theory that allows you to analyze those questions and make more reliable predictive claims. But if we wanted to get to this thing we've decided is better, here's positively, predictively, what that might need to look like.
What are alternatives to norm-based or normative approaches that we can compare and contrast your set of approaches with?
I don't know if the person who asked this wants to say a little more, because I think there are lots of different ways of, lots of people have will invoke norms. If you're talking about safe, aligned, beneficial, cooperative AI, you're invoking norms. You're invoking this is okay and not okay. This is a good way to arrange things. This is a good way for an AI system to behave, not behave. RLHF, right, is the fine-tuning on language models is normative. And so the contrast I think you get is between what are the systems we're using there for thinking through what it means to align or get the values we want. And I would say the distinction here is, I don't know. I mean, there is the 2014 paper talks about the different theories of law, and so you could look there for, say, what the comparison is. As I started with, I sort of feel like it's shooting fish in a barrel to compare this approach to other approaches, because they're really not theoretical, and they tend to be atheorized. They don't have a theory, and they tend to be heavily normative as a starting point, in the sense of the world should be democratic. So how would we make this democratic? Or they start with something, I know you were learning more about social choice theory and aggregation of preferences. So that will be a theory that says we should elicit from individuals what their preferences are and identify what, we should find a way of aggregating those preferences and selecting which ones to align to. Again, our LHF is sort of doing that by hiring labelers and instructing them. So I think you could compare that. Maybe some tests would be, would a system designed according, using the theory that I'm creating here, produce systems that were more stable, systems that produced higher welfare, that's what we actually were testing, and systems that were deemed more acceptable to populations. So that's other work that I do, is to think about how could we connect more with ordinary people and find out what they want systems to look like. So whoever asked that question may want to follow up with me later, because I may not have quite understood where you're coming from.
Are there norm-related evaluations we should require systems to pass before being deployed?
Well, I think the answer is clearly yes. And again, you could frame that question as, I have a normative stance, I have beliefs, I have principles, and I want my AI systems to follow my principles, right? I could start at that normative stance. The stance I start with is stability. That's a positive concept. That's not I, as the designer or the researcher, saying what I think is good or bad. It's me saying, number one is we need this to be stable. I also think it's important, and this is something I really, when I was sort of, wave my hand around the room and say, like, this room is filled with millions of normative classifications. There is a tendency to sort of, there's sort of ground truth, there's baseline, and then there's some norms we might throw on top. Equality, autonomy, non-discrimination. But I want you to think about normativity as just like we are swimming in a dense sea of normative classification. And that's actually the secret to why humans are so successful, because we actually classify almost everything. So I don't even know quite what would it mean to not be thinking about, of course you want AI systems to be participating, complying with norms. I also think participating in enforcing norms.
Just as a point of clarification, can you say what an evaluation for stability might look like?
Yep. So we have an earlier paper that looked at the robustness of groups. We just did this in a repeated game context and it's sort of a partially observable Markov decision process. Every agent in the group is deciding, am I going to stay in this group, or should I go to my island in each period? Staying in the group is valuable if there's an important, there's rules in the environment. There's one important rule. Staying in the environment is more valuable than the island if the rule is being enforced. But there's uncertainty there can be a shock to the community about whether or not there are a sufficient number of enforcers in the population. So the size and composition of the population is changing over time. And what we're able to look at, so the metrics we look at is the size of the community. Is it losing membership because people have the choice to leave? And if enough people leave, it just collapses, because once it gets to a certain size, then nobody wants to be in the group and everybody goes. And we're able to actually show, we also tested the silly rules hypothesis there and saw that the societies with lots of silly rules as well as the important rule, maintain population and were more stable. And so that's stability. They maintained population, they didn't collapse. So that's a way of thinking about stability of the group. So then they could generate the benefits. And what was key there is that they suffered a shock to beliefs that was not a shock to the underlying ground truth. You can imagine that a bunch of newcomers joined the group. We don't know about, we're uncertain about these newcomers. Do they help enforce the rules? Right? Well, the fact of the matter is they do. And you want the group to quickly learn that so that it doesn't freak out and everybody runs away and, lives on their island.
We are now at time, so one more round of applause for Gillian, please.
Thank you.